Now in this part of the video we're going to consider this general case. So C is S units more than B. So S can be any positive integers. Well, I guess our current goal is describing this set of triples x, y, z and integers that satisfy this Pythagorean equation theorem, so that you actually describe it in terms of parameters. So one of the parameters, I'm sure, is kind of related to this variable s we're putting in, the relationship between b and c, described as s unit apart. So that's our goal. So this is a condition statement, and this is more of a generating method. So this is our goal. But it happens that there are a lot of cases, and from that cases we have to reduce this cases by factoring, canceling this common factors across this x, y, z, which is allowed if you look at these equations. So it turns out it's better to look at something called primitive solutions. So primitive solution is these Pythagorean triples, so there are no divisor that is greater than 1 that divides all this x, y, z. And x and y may have a common factor greater than 1, but that is not going to divide z. So that's what we mean by GCD of these three numbers. So when we look at our when you arrive to the final shape of our calculation, and if we just look at this primitive solution, that reduces a lot of argument that without it you have to go through these cases and lots of reductions. So we're going to focus on these type of solutions called primitive solutions. So we're going to start like this. We're going to let this p x with the coordinate x0, y0, z0 to be a primitive solution, and our goal is describing each of these coordinates from this Pythagorean triples using other integer parameters. So here's the way we approached from the early examples. First, we focus on the difference of these two coordinates, y0 and z0. So focus on this could be some integer s. So here I'm going to let this difference to be s here. In the earlier example, we looked at 1 and 2 as an example. So we're here general setting. So here's the same approach. We substitute z0 with y0 plus n and expand to pull out linear relation on y0. So which is this one? We expand it and cancel these two y squared, and we have this linear relation. And before we solve this one, we introduce another parameter. So that that's the idea. This is a difficult part, and squared and treat it as another parameter. So x0 equals t. That's how we approached it early example. So if you solve for y0, and y0 is written in terms of s and t now. So here it is, y0 is in terms of s and t. Although it looks like irrational numbers, we started with a primitive solution. This is supposed to be an integer solution, however that cancellation works. These there exists, so to summarize up to this point, the point is if this is a primitive solution, then there is this integer s, and there is this integer t, such that y0 is described in this way. And if you go back to z0 and use this description to write down what z0 is, y0 plus s, therefore adding s here is the same as adding 2s squared in the numerator. So it's going to be ts, 2s squared added to that. It's going to be a positive 1 copy of positive s squared, and the denominators are 2s. Alright, so I'm going to get rid of that. So it is. But if you think about the divisibility in this setting in here, in this shape, it turns out a little bit more inconvenient than next step. Next step is a really nice trick that we actually look at different solution, not this one, non-primitive solution possibly. So we have this x0 and y0 and z0 described like this with s and t, but we're going to enter x1, which is, let me write down that equation over here so that you can see what I'm doing. So here it is. I wrote those solution, now this different shape of the solution rather than just x0, y0, z0, we describe those primitive solution using these two integers s and t in this way. Then I'm going to enter a more polynomial looking equation by multiplying these denominator, which is here the 4s squared, but you can put them inside the square, so it's still 2s in there. So I'm going to multiply through 2s squared there. So I wrote it like this. So maybe I'm going to go to the other side. I'm going to continue it over here. If you multiply to that part, you have this 2st inside now, it's squared. If you multiply to that, you can see that denominator cancels. That's the whole motivation. So we have t squared minus s squared in there. And this one cancels the denominator. We have t squared plus s squared on the right hand side. So this is not necessarily primitive solutions, but it's quite related to primitive solution we want to describe. So here's x1, that's going to be 2st, and y1, and that's going to be this solution, and z1 is going to be the third one. So what we have here is a multiple of a primitive solutions. So if you can figure out what to divide through and come up with a better integer description, parameter description, that'll be the description of a primitive solutions. So now one observation at this point is that if s and t has a common factors, then it's always going to contribute to the common factor throughout the entire solution set in here, x1, y1, z1. I meant entire coordinates, all three coordinates involved in the solution set. So maybe that's the first things to go after. So get rid of this common divisor of s and t that contributes to common factors in here. So let's write d to be common divisor of s, the greatest common divisor of s and t, and you write s as d times m, for example, and t is d times n. And then it's going to be d is going to be the common factors. You can see you can get rid of those common factors here. And so I'm going to rewrite x1. x1 is going to be now 2 times, if we multiply these two, we have d squared factored out. So we have 2 times m times n. It's a nice structure, something called homogeneous terms, and throughout this equation allows you to have this nice cancellation with a nice scaled kind of substitution. So let's look at y1 here, running out of space. Let me create the space like this. y1 is going to be dd, it's common, so it's a d squared pulled out. So we have m squared minus n squared. And z1 is now the same thing with positive inside there, so d squared m squared plus n squared, if I can fit in. Now if I let this p1 to be this x1 and y1 and z1, and potentially there is this greatest common factor of s and t that is greater than 1, and that it's exhibited here. So if I knock those down, we're one step closer to our primitive solution. Remember, this x1 and y1 z1 was obtained by multiplying this factor 2s throughout this primitive solutions. So we're canceling some of this common factor that we structured out, so that's one step closer to the primitive solution. So let's write that out. So d squared is common, so I'm gonna so maybe I'm gonna call this, I'm gonna knock this one out. It's unnecessary to write it in here. We're gonna let x2 being 1 without d squared, so it's gonna be 2mn, and you have to imagine that that's still, because d squared is throughout this common, if after you cancel those, these x2 and y2 z2 will be still solutions. So let me just write that down first, like this. z2 is m squared plus n squared. There's still a solution because this is a solution, and d squared shows up everywhere. Actually, d to the 4th shows up as u squared. You cancel all that, and then you obtain an equation that in terms of x2, y2, z2. So namely, if you write it like this x2 squared plus y2 squared, z2 equals z2 squared, because the common factor cancelled. So we have another Pythagorean triple closer to our primitive solution, and they're described by this parameter where this m and n is no longer have a common factor. Now I think it's reasonable to ask this question: if I label this point P2, how close is P2 to this primitive solution? Remember how we generate this x2, y2, z2 is to multiply through some constant integers, and in a very special way we've factored out some of the common factors. So have we eliminated all the common factors? That's what this question is asking. And we're going to examine by looking at the shape if it's possible if there's a common factors across this x2, y2, z2. And because of this 2 involved in here, it turns out if you consider first odd common prime factor involved in here, that it's kind of easier to conclude. So let's start with the first part, which is there an odd common factor? Alright, here's written down: is there odd common prime factor P in this solution x2 and z2, y2 and z2? So because it's odd, if it divides this one in here, so suppose there is, then it's going to divide either m or n. Say, to start with, say P divides m, that's a symbol for dividing. Then because P divides m, so that's going to divide this term, and P is a common factor, so that divides y2, so that must divide n as well. So if you add the factors, P divides y2, because P is a common prime factor of all these things, P divides m and P divides y, that forces P divides n. But we know that we already have this condition that mn has no common prime factors, so that's a contradiction. So we can easily eliminate the possibility if there's any odd prime factor. Alright, let's consider the possibility that whether there is going to be an even factor even though we have this condition m and n being relatively prime. So is the statement about there's an even factor, so it's a good idea to reduce that calculation to mod 2. So I wrote down all possibilities of parity of m and n, and what could happen to these values, m squared, n squared, like that. So this means m and n are even number, and even and odd and even, and odd. Those are the possibilities of m and n. I squared it, so that wrote down the square version so that you can easily see this m squared minus n squared, m squared plus n squared in here. Of course, we're looking at the version m and n are relatively prime, so we're not going to consider even that row here, where both m and n are even numbers. So we'll eliminate that. Sorry, it shook a little bit. So if you look at this case, where the m and n are an opposite parity, one is even and the other is odd, then for both cases, as you can see, m squared minus n squared, which is a y value, y2, m squared plus n squared is a z2 value, right? That's involved in here. Those values are odd values, so it does not have a factor of 2, so that's actually good. These two cases would be good if when m and n are different parity, then there will not be any common factor of 2. So that's the one thing. So let's record it here. The best way to record it, m and n on mod 2 is different, not 0, 0, 1, 1. That's the best way to. So then, together with this conclusion, we know the solution x2, y2, z2 is primitive. So now it is this case in here that we have to take care of. So we are looking at this case, m equals and n, both are congruent to 1 mod 2. So miraculously, we can rewrite this solution set in here exactly back to this shape, which can be discovered by just writing m as a 2a 2s plus 1, n being 2t plus 1, and something like that. But after you go through all that calculation, you might discover the following trick, which is not easy to pull out at this stage, but you might come back in and pull out this type of solution later on. So here it is. The first thing is that if you can look at the examples where this m and n are odd numbers, and if you plug it in here, you can see there's everywhere 2, it actually cancels. So when you cancel that 2 in here, then you're going to lose that 2 in here. So you're not going to keep the structure like this. So you have to wonder that if you can still rewrite after you cancel those 2, wonder if you can rewrite the solutions, integer solution, back into this form. So here's the trick. So the first observation is that second part here, y2 is written like this, m plus n times m minus n, and when they're both even numbers, odd numbers like this, and this is even number and that's odd number, that's both even numbers. So we can write it like this, m plus n being even number 2a, and m minus n being even number 2b. Then if you rewrite the entire thing in terms of a and b and canceling the common factor of 2, it turns out we go back to this shape. So let's rewrite it. x2 here is 2 times m. So here, if you add this to equation and divide it by 2, you can see this m is a plus b. And n is subtracting this one, subtracting this equation from the first equation and divided by 2, then that's going to give you n, so that's a minus b. So you already can see that before you have this difference of squares showing up in the second part, but this time we're having those difference of squares showing up in the first part, is kind of switching the role. So y2 is here, already written m plus n, that's already 2a. 2a there, and a m minus n, that's 2b, so you write it like this. Alright, so that's that, and z2, going back there again, and here, maybe write it down. If you solve for m and n, m was a plus b, n was a minus b, right? So that was the idea. So if you put it in here, in the z part, m is a plus b squared and a minus b squared, and here's a plus. So when you expand them out, 2ab and negative 2ab cancels, you have a 2 times a squared plus b squared. So it's miraculously kind of recovering the shape by switching its role. Now finally, if you observe that there's a common factor there of 2 appearing in here and 2 appearing in here in this form, 2 times ab, and keeping that 2 there, and here's a 2 appearing there. So you can cancel all this common factor and come up with a new solution, a reduced solution, which is, I'm going to write x3, so that's going to be, if you expand this one without that 2 in there, after you cancel, is a squared minus b squared. Y cubed is with that 2 cancels, a 2ab, and z3, not cubed, and is a squared plus b squared. So if you compare this one with the earlier parameterization, that's exactly the same shape. And because, and more importantly, we keep this property A and B are relatively prime to each other, because if there is a common factor, that appeared as a common factor of m and n there. So it's fairly easy to prove it, but it's important to observe that A and B is still relatively prime to each other after you do this reduction. So what we have accomplished here, if there is a common factor of 2, you can get rid of the common factor, you can still keep this form exactly. So if you keep repeating this process of eliminating only potential common factor of 2 in here, keeping this condition, you eventually get down to this 2 of this condition in here. Because if it is A and B are both odd, then there is still going to be a common factor of 2 after you get rid of it. if there's still common both odd and A and B, then you keep reducing it, and you will eventually reach the condition that it does not have a common factor anymore. Then it means that these m and n here, in this case an A and B, will eventually become opposite parity in there. So that's the final conclusion. We can write down the primitive solution x0 and y0 and z0 into the following shape, where 2uv is both an integers and u squared minus v squared and u squared plus v squared, where we keep this condition uv is relatively prime and u and v is always opposite parity mod 2. So we arrive at here, and showing that this condition actually generates a primitive solution is relatively easier. So we're going to stop in here, and now what's the reduction at the end? This mod 2 calculation got a little bit complicated, but it's actually an important part of this calculation.